In my previous video on the tensor formalism of electrodynamics, I talked about the concept and the idea of a forecurrent. And we also discussed the continuity equation of electrodynamics in 4 vectors. So in this video, I'm going to completely formulate the electrodynamics in tensor notation with the help of the electromagnetic field strength tensor and its corresponding dual strength tensor. So our goal would be to first derive these tensors and then see how do we recover the 4 Maxwell's equations from it. Right, so in the Gaussian units, the Maxwell's equations are written as follows. So let me write them down. So we have the gradient of E is equal to 4 pi rho, right? Rho is the charge density. So let me number them. Then I have my gradient of magnetic field, which is equal to 0, and let me call this equation number 2. Then I have my curl of E, so that's this thing, which is -1 over c times the time derivative of my magnetic field. So let's call this equation 3, right? Okay, and finally we have the curl of magnetic field, which is equal to 4 pi over c times the j, that is the current density vector, plus 1 over c times the partial time derivative of my electric field E, right? And so I'll call this equation number 4. Right, so let me mention this again, that these 4 Maxwell's equations are written in Gaussian units here, right? So if you look at these equations, they consist of a set of coupled first order partial differential equations, right? Which are relating the various components of the electric and magnetic fields. Now from electrostatics and magnetostatics, we are familiar with the concept of a scalar potential phi and a vector potential A, right? So my scalar potential is phi and my vector potential, that is A, right? So since we know from the second Maxwell equation that the gradient of magnetic field is 0 or it vanishes, so then there should be a quantity whose curl is actually my magnetic field, right? And so let's go to the next page and write that my magnetic field is then equal to curl of something, right? And that something is then my vector potential, right? Okay, so now I'm going to call this equation alpha. Right, now in Maxwell's equations, that is curl of E, let me go back here. If you look at this equation, that is equation number 3 from here, we have -1 over c times the partial time derivative of the magnetic field. But we defined our magnetic field in equation alpha over here as the curl of some vector potential. So let's write this down as -1 over c time derivative of the curl of my A, right? Let me put these vector symbols. Right, okay, now we know that the partial derivatives commute, and so I can exchange the positions of these two derivatives, right? And so let's go ahead and do that. So we have curl of E is equal to -1 over c, and let's change these positions. So we have the curl of, or let me actually write this down. Let me actually take this curl thing outside. So I have this curl of E and this curl of A, right? So what I can write this as my curl of E, and this quantity is negative, so if I take it over there it will be positive, so positive 1 over C times the time derivative of my vector potential, right? And so on the right hand side I will be left with 0. So this equation over here, I'm going to call it as equation number 1, the Roman 1 capital, right? Okay, so if you look at this equation, this equation has a solution that is E is equal to negative gradient acts on my scalar potential phi minus 1 over C times the partial time derivative of my vector potential A, right? So this is the solution to equation number 1 over here, right? So let's go ahead and call this equation as equation number 2. Okay, so then this definition of magnetic field, that is in equation alpha, and the electric field, that is in equation number 2 over here, in terms of these potentials A and phi, it satisfies identically the two homogeneous Maxwell's equations, that are the Maxwell equation 2 and 3. If you go back here, the equation number 2 and equation number 3, right? So now let's go to the next page. The dynamical behavior of vector potential and phi, the scalar potential, will be established by the inhomogeneous Maxwell's equations, that are the Maxwell equation number 1 and equation number 4. So if you want, I'd go back here and you can look at these equations. So equation number 1 and equation number 4. Now equation 1 and 4 can be also written in terms of my scalar and vector potential. So let me go ahead and write this equation 1 and 4 in terms of scalar and vector potential. So I can write them as the gradient of, now let me actually go back here. I'm first going to write this equation 1, right? And so it has gradient of E is equal to 4 pi times the charge density. But we just figured out the solution to our equation number 1 over here, that was E. So I can substitute for E as this equation number 2. So the gradient of negative del phi minus 1 over C partial time derivative of A, that is the vector potential, right? And let me add these vector symbols. Okay, this is then equal to, from the first Maxwell equation, 4 pi times rho, right? And now I can distribute this del, and so I'll have negative Laplacian of phi minus 1 over C. Now again, because my partial derivatives commute with each other, I can have this thing as partial time derivative of my gradient of vector potential A, right? And on the right hand side, obviously we have 4 pi times rho. Now let's call this equation equation number 3, right? Okay, so moving on, now I will use my equation alpha and 2 in Maxwell's equation 4. So look at this equation. Alpha is for my magnetic field and equation 2 is for my electric field, and Maxwell's equation number 4 is over here, right? So I'm just going to substitute for B and E from my equation alpha and equation 2. Right, so let's go ahead and do that. So what I would have is my curl of A is equal to 4 pi over C times J plus 1 over C partial time derivative of negative del phi minus 1 over C partial time derivative of my vector potential A. Right, so all I have done so far is substituted for my in Maxwell's equation 4 over here. I have substituted the value of B and E from here. So B is this and E is this, right? Okay, so let's move on and simplify this a bit more. So we know that this thing over here evaluates to the gradient operator of the divergence of A, that is the vector potential, minus Laplacian of A is equal to 4 pi J over C plus 1 over C partial time derivative of my this thing over here, that is negative gradient times phi minus 1 over C times the partial time derivative of A. Right, now let's move on and distribute this del in here. So we would have the Laplacian of my vector potential A plus, now I'm also moving some terms here and there, so I would be having on this side, I'll be taking my this term over here multiplying with this, so I would be having plus 1 over C squared partial time derivative squared of my vector potential A. I'm sorry, I said that I will be distributing this. I'm not doing that, right? All I'm doing is writing this over here, right? So there will be a negative sign over here, and so let's continue this A vector, and all of this would then be equal to 4 pi over C J vector, that is the current density, minus the gradient operator and this thing over here, right? So now I'll be writing this thing as del dot A minus 1 over C times the partial time derivative of my del of phi, right? Okay, so my goal is now to write this equation or this expression in terms of this on the right hand side. So I would be just bringing all of the other terms to the other side. So let's go ahead and do that, right? So the next step from here is then negative, or actually let me do it on the next page, right? So negative Laplacian of A is okay, plus 1 over C squared partial time derivative squared A is equal to 4 pi over Cj minus, now if you go back here, what we can do over here is take this because again the partial time derivative and this gradient operator commute with each other, we can take factor out this operator del, right? So let's do that. Minus del of del dot A, that is the divergence of A, plus 1 over C partial time derivative of my scalar potential phi. Right. Now let me just go ahead and bring this term over here, right? So when I do that, what I'm left with is my Laplacian square A minus 1 over C squared partial time derivative squared A minus the del operator and the divergence of A plus 1 over C partial time derivative of phi. All of this is equal to this thing over here, right? So 4 pi over C times J vector. Right, and so I'm going to call this equation equation number 4. Right, okay, so now the equation 3 and 4, let me go and show you. This equation number 3 and equation number 4 have essentially reduced the set of 4 Maxwell's equations into 2 equations, but there is still a problem that they are still coupled equations, and now our next task is then to uncouple them, and to do that we would need something that is called the gauge transformation, right? Okay, so let's go ahead and recall from classical electrodynamics that the gauge transformation transforms vector potential A to some A vector potential plus some gradient of your lambda, which is the transformation, right? Now let me call this transformation A. Right, now this transformation does not affect the equation that was B is equal to curl of A, right? So that is very important for us, right? So the transformation should not affect the equation, right? And so for the scalar potential, the gauge transformation is your phi is transformed to some phi prime, which is actually equal to phi minus the partial time derivative of your vector potential A. I'm sorry, not your vector potential, the transformation, right? So this I'll be calling B, equation number B. Okay, so likewise this should also not affect the equation for E, which was E is equal to negative gradient or negative this thing del operator of phi minus 1 over C times the partial time derivative of scalar vector potential A. So the transformations should not affect these equations, right? And they do not. So the transformation that we have taken, they do not affect these equations. Now this freedom allows us to choose a set of potentials, that is a set of potentials A and phi, right? Such that my gradient of A plus 1 over C times the time derivative of my scalar potential vanishes, right? So this over here is going to be really useful now. So now if I call this equation C, right? And I use equation C then in my equation number 3 and 4, which is this is equation number 4, and over here this is my equation number 3, right? So I'm going to use this C, equation C, in my equation number 3 and 4. So let's first substitute this for equation number 3. So actually let me write my equation C on top here. So that is again the gradient of A plus 1 over C partial time derivative of phi is equal to 0. Right. So now I'm going to first substitute this for equation number 3, right? So in equation number 3, so then I would have the negative Laplacian of phi minus 1 over C times the partial time derivative of negative 1 over C partial t phi is equal to 4 pi rho, right? And now this then can be reduced to this thing, negative Laplacian of phi plus 1 over C squared partial time derivative squared of my scalar potential phi is equal to 4 pi rho, right? Okay, so then the next step is to just write it down actually neatly. So we would have 1 over C squared partial time derivative squared phi minus del square phi is equal to 4 pi rho, right? So this is what I have for my equation number 3 with substituting with this equation number C, right? Okay, so if you look at this equation, it's going to turn into a form of the D'Alembert operator, right? And so hence the equation number 3 and 4 would be reduced even much more, right? And so we would see that. So keeping this equation in mind, right? Now second, let's go to equation number 4. So let me actually go back. This is our equation number 4, right? And so we are going to again use the equation number C in this equation number 4. And when we do that, let me go to the next page. What you get is, if you look, the Laplacian of A minus 1 over C squared, the time derivative squared of your vector potential A is equal to negative 4 pi over C times the current density vector J, right? Okay, so now let's just move the terms, and what we get is 1 over C squared partial T squared A of, this is the vector potential, minus the Laplacian of vector potential is equal to 4 pi over C J, right? So I have just rearranged this equation over here to get rid of this negative sign on the right hand side, right? So now what we can do from here is then we have this A, so we could factor that out, or we would factor that out on the right hand side actually. So we would have 1 over C squared partial time derivative squared minus Laplacian. This is an operator now which acts on your vector potential A and returns with 4 pi over C times the current density vector J, right? So also we derived likewise for the scalar potential that is over here, right? So let me then write it down over here. Actually, I'll write down the equation or expression we had for scalar potential as well. So that was this thing over here, minus Laplacian acting on phi, giving you 4 pi rho. Right, now if you recall the D'Alembert operator, so in other words, then we can write these two equations as follows. So I can write them down as operator acting on A and giving me 4 pi j over C, and then likewise for scalar potential phi and giving me 4 pi rho. Right, so these are now our two equations, and if you look at them, they are now uncoupled, and also the four Maxwell's equation have been reduced to only two equations, right? So we have achieved a task of reducing the Maxwell's equation and uncoupling them, right? Okay, so I can then write them in a covariant form as this D'Alembert operator A alpha is equal to 4 pi over C and the covariant or the contravariant vector J, right? So that is the forecurrent density, right? So again, this is the covariant form of my these two equations, right? And so I can then define my A alpha as the time component of this tensor is then scalar potential, and the spatial components can be written as the vector potential, right? Okay, so then likewise the Lorentz condition in covariant form will be written as partial alpha A alpha is equal to 0, right? Okay, so we can then explicitly write down the x component of equation alpha and equation number 2. Let me go back. So this over here, yes. This over here is my equation alpha, right? And equation 2 is this one, right? So now what I can do is I can explicitly write down the x components of my magnetic field and the electric field using the covariant form of this equation, right? Using this equation over here, right? Okay, so let's go ahead and do that. If you carefully look at this equation, you can see that the time component you would have from here, that would be your scalar potential, and the other components, that would be 1, 2, and 3, would come from this vector A. That would be AX, AY, and AZ, right? So let's move on. Now first let me write down my x component of the electric field as is equal to, now note that I'm writing the x component of my electric field, right? So that would be written as 1 minus 1 over c times the time derivative Ax and by the way, note that I'm writing this equation for E from this let me go back, yeah, this equation number 2 over here, right? Okay, so let's go back. So I have ax minus the x derivative of my scalar potential phi. Now if you look at this equation over here and look at this equation and this one, right? So you can then see that this part of the equation is simply your zeroth component of the derivative, right? So it's partial zero, and this one is then a1, right? So that is ax. Then you have the negative sign. Again, this component of the 4 gradient is then partial 1. And if you look at this phi, that is simply your a0, right, from this over here. So if the zeroth component or the time component is the scalar potential, so then I have a0, right? And this is obviously the x component of the electric field. And let's go ahead and call this equation F, right? Now likewise for the magnetic field x component, if we go back over here to equation alpha, right? So that is the curl of A, right? So which can be written as the partial derivative with respect to y of az minus partial derivative with respect to z of a y. So that is the x component of the magnetic field, which can of course be written as in the covariant form as this is partial derivative with respect to y, so that would be partial 2, right? And then we have a z, so that would be a3 minus now partial z, that would be the partial 3, and ay, so ay would then be a2, right? Okay, so let me get rid of that arrow. Okay, so this of course the x component of magnetic field is this thing times multiplied by 1, right? So we are actually taking the curl of the, let's go back here, taking the curl of the vector potential A, right? Okay, so the next step is then to write this equation over here, that is for the magnetic field. Let me actually go ahead and call it equation G. So the next step is now to write equation F and equation G in a single equation, right? And we can obviously do that, right? Because if you look at equation F and G, they're just they're actually a single equation, right, with different components of the 4 gradient and the 4 vector, right? So writing them in a single equation gives me partial alpha a beta minus partial beta a alpha, right? And so this expression over here is, I'm going to call it, is equal to f alpha beta, right? And of course with my partial alpha is equal to my partial x derivative, the zeroth component of x, right, and negative gradient. Right, now this expression over here is called the field strength tensor, right? So this is my electromagnetic field strength tensor, and we can write it in the matrix form as F alpha beta is equal to, now let's write down all the components. So we would have F00, 0, then F01, F02, and F03. Now likewise here we would have F10, F11, F12, F13. Now F20, F21, F22, F23, and F31, F32, F33, I'm sorry, I would actually have over here F30, right? And F31, F32, F33. Right. Okay, so this is then the matrix form of my field strength tensor. So obviously the next task is going to be to work out the components of electric and magnetic field from this expression or this equation right here. Let's call it equation H, right? So from equation H. So if you look at your equation H, or the equation for the field strength tensor, you have partial alpha A beta minus partial beta A alpha, right? So upon examining this equation, it is obvious that if you would have alpha is equal to beta, this expression or the equation would vanish, right? So the left hand side would vanish, because let's see, right? Let's see. Okay, so we would have F00, right? The first component. So what would that be then? According to the equation, that would be partial 0 A0 minus partial 0 A0, right? And so obviously this vanishes, right? Okay, so now let's look at the component F01. So what would that be? That would be partial 0 A1 minus partial 1 A0, right? So if you go back over here, so from this expression, what is your partial 0, where alpha is equal to 0? That is simply this one, right? So partial with respect to x0, right? So here I would have my partial with respect to x0, and a1, let me write it down as a1, negative, and now partial 1, right? So what's that? That is simply my negative a gradient, right? And so a gradient is a vector, so it would be in x, y, and z, right? So I would have here my partial x1, right? Okay, so a0, right? And let me actually go over this thing again. What I simply did is this partial superscript 0 I have from this equation over here. That is this right here, right? So that's the time component of my foregradient. And for this partial 1, if I go back here, I have this thing, but this is actually distributed over all the components, right? So it has x, y, and z. And so x we write it as 1, y as 2, and z as 3. So if you go here, I wrote it as x1, right? Because it is partial 1, right? So that is then the x component of the spatial part, right? Okay, so we also know that the partial x1 is actually simply my negative partial x. Now this x is for the x, y, and z, right? And so using the convention for the metric tensor as the we call this the particle physicist convention, which is that your time is positive and spatial components are negative, right? So using that convention, we can have the 4 gradient component as this, the x1 component, right? Okay, so therefore my f01 can be written as simply partial x0 a1 minus partial x a0. Now this can be further written as note that partial x power 0 I'm sorry, that's not power 0, that is the contravariant 0th component of my x, and we know what that is 1 over c times the partial time derivative, right? And we have a1, so let me write down here a1 minus the partial derivative with respect to x, that is the spatial component of my a0. Now let's go back here and see where I defined my a, right? Yeah, over here. So your a alpha is defined as this. So for a0 it's phi, and for a1 or a2 or a3 it is then the vector potential a. So that would be distributed for in components x, y, and z, right? Okay, so with that then I can obviously write this down as 1 over c times the partial time derivative of my a1 minus the derivative with respect to x, and a0, which is my scalar potential, phi. And so this is then my f01 component, right? Now if you recall from your equation number 2, that was for the electric field, let's go back, this equation over here, that is negative del phi minus 1 over c times the partial time derivative of a, right? And so which is actually almost completely similar to the expression that we got for our 0, 1 component, right? This thing over here. So I'm sorry, we would be having plus over here, right? Okay, and of course again we would be having plus over here. Why this plus sign? Because there was this negative sign with this partial x, right? And so I forgot to add that negative sign in this equation. So with that negative sign, the negative and negative over here becomes positive, right? Okay, so this is the equation that we have, which is almost similar to the electric field equation, that was equation number 2, except for the negative sign, right? And so if I add for the negative sign, what I get is that my f01 is equal to negative e, but if you go back here, you look at this equation, this is for the x component, right? So you have a1, which is again the x component, and you have this partial derivative with respect to x. So this would be your x component of the electric field. Right. Now, likewise, you could figure out f02 and f03, right? And so what you would get is negative ey and negative ez, right? Okay. Now, due to the symmetry, what you have is your f10 would be ex, f20 would be ey, and your f30 would be e. Z. I said symmetry, it is actually anti-symmetric, right? Okay, so we have figured out a lot of components, right, except for the fact the 1, 2, 1, 3 and those components, right? So let's go ahead and do that. So if you have to write the component F1, 2, what would that be equal to? So again, recall from the expression for the field strength tensor, we would have this as partial 1 A2 minus partial 2 A1, right? And then again, if you remember what your partial 1 was, that is simply partial derivative with respect to x1, right? So that is then the x component. And A2 is your AY, right? AY minus the second component of your 4 gradient, which is simply partial x2, and the first component of your scalar vector potential, right? And so that is simply AX, right? Okay, so now if you recall your equation alpha, that was simply the curl of A is your magnetic field B, right? So this expression over here is actually your curl of A, right? Actually it is the negative times the curl of A with Z component outside, right? So then I would have this equation as simply the negative curl of A, right? This thing over here. Okay, so what this is then the zth or the Z component of the magnetic field, right? The negative of the magnetic field. So my F, or I'm going to do it over here, right? On this side. Okay, so if you look at this, right? This is similar to this, except for the fact that it is the Z component and there is a negative sign over here, right? Okay, so then your F1, 2, F1, 2 component is simply the negative B in the Z direction. And so likewise you could compute F13 and F23, right? So what would those be? Those would be F13 would be your BY and F23 would be your negative BX. So you could do this as an exercise. You would follow the same procedure that I followed for computing part F12, right? And you would go on and compute F13 and F23. Right. Now let's go ahead and because we have figured out all of these components of the field strength tensor, let's go ahead and write down it in a matrix form, right, with the components. Now here I would like to pause and mention that if you're watching this video, it is recommended, highly recommended, that you should sit down and perform these calculations with yourself with your own hand, right? And so that is how you would understand what is actually happening over here, right? Because the calculations look pretty crazy, but once you start doing them yourself, you understand what is happening and why is it happening, right? Okay, so let's get back to our task and write down the matrix form of the field strength tensor, right? So let's say that it's F mu nu and write down its matrix elements, right? Okay, so we figured out that whenever your mu is equal to nu or alpha is equal to beta from your equation H, when the alpha and beta would be equal, the components would vanish, right? Okay, so what that means is then all the diagonal terms of this tensor would vanish, right? Or let me like this. Yes, okay. So and all of the other components we figured out as let's go back over here. So f01 is negative ex from here, f02 is negative ey, f03 is negative ez, and so then later on we have for f10 and so on, right? So let's just substitute these in here. So we would have over here f01 as negative ex, f02 as negative ey, and f03 as negative ez. And likewise, substituting all the components, we would have ex over here, ey over here, and ez over here, right? And bz over here, negative by, bx, negative bx, by, and negative bz. Right, okay, so all I have done over here is, if you go back over here, we wrote the field strength tensor in the matrix form as this. And so after this, what we did was we worked out these components f00, f01, and so on over here, right? So here is where we worked out these components, and then all I'm doing is substituting the solutions or the answers we got for those components. And so we can now directly work out the Maxwell's equations with the aid of this field strength tensor, right? Now let's go and see how can we do that, right, on this page. Okay, so for the Maxwell's equation, we can now write that my partial alpha f alpha beta is equal to 4 pi over c and j beta, right? So from the forecurrent, we know that the zeroth component of this forecurrent is my charge density, and all the other components are my ordinary current density, right? And so now we have the Maxwell's equation in this single equation over here, right? So we would see that we would be able to derive two of the Maxwell's equation from this, and then we would find or derive or define another quantity that is called the dual field strength tensor, and we would figure out the other two Maxwell's equations from that. Right, now all we have to do here is first substitute for beta is equal to 0. Right, so once we do that, we get this equation as partial alpha f alpha 0 is equal to 4 pi over c and j 0, right? Okay, so now if you remember, we sum over the repeated indices, and so what we would have this as partial 1 f10 plus partial 2 f2, I'm sorry, we would start from the 0th component, right? But anyhow that would vanish, right? Because we would have part f00, and then we would have plus partial 1 f10 plus partial 2 f2 f20 plus partial 3 f30, and all of this is equal to, of course, 4 pi over c times rho, right? Because that is the zeroth component of your forecurrent, which we defined in our previous video on the forecurrent, right? And we have an c as well, right? So now let's go down and let's see first that this thing vanishes, right? It vanishes because the f00 component vanishes, and so this derivative would of course then vanish. Okay, so let's look at this one. So this component is its partial one, so that's partial derivative with respect to x. f10 we figured out was ex, and likewise we have for this partial 2 is then partial y. f20 we figured out it was ey plus partial 3, which is partial z. f30 likewise was ez, and this is equal to 4 pi, c cancels over there, so we are left with 4 pi rho, right? Now if you look at this equation, the left hand side is simply the gradient of E, right? So gradient of E, right? Because gradient is the partial derivative with respect to x plus partial derivative with respect to y plus partial derivative with respect to z, and obviously their corresponding basis vectors I hat, j hat, and k hat. And so when we dot that with E vector has ex component in ith direction, ey component in jth direction, and ez component in the kth direction. And so when we take this dot product or the gradient of E, this is what we get. So we can write this now as the gradient of E and equal to this quantity over here, which is 4 pi rho. And if you recall, this is nothing but your first Maxwell's equation. So we have essentially recovered first Maxwell equation from the electromagnetic field strength tensor by substituting for beta is equal to 0, right, in this equation. Right. Okay, so the next step would be now to substitute beta is equal to 1. So let's go ahead and do that over here. Now if we take beta is equal to 1, right? So what we would get? Well, we have partial alpha f alpha 1, right, is equal to 4 pi over c j1, right? Because we are substituting for beta is equal to 1. Now likewise, just we would sum over the repeated indices, so we would have partial 0 f01 plus partial 1 f11 plus partial 2 f21 plus partial 3 f31, and this is of course equal to 4 pi over c and j1, right? j1. Okay, so if you look at this equation, we know that f11 is 0, it vanishes, so therefore this term would go to 0. And now let's see this term. We know that partial 0 is nothing but 1 over c times the partial time derivative, and f01 we figured out as negative ex. So actually let me take out this negative sign outside, and I would have ex over here. Then plus for this term partial 2, which is nothing but a partial derivative with respect to y. f21 is bz, right? That component was equal to bz, plus partial 3 is nothing but my partial z, right? And f31 was negative by. So let me take that negative sign outside. I would write it over here, and I would have by. And of course all of this is equal to 4 pi over c j1. Right. Okay. Now what we can do from here is, if you look at this part of the equation, right, that is nothing but your curl of b, right? And of course the x component of that, right? So then what we would have is minus 1 over c partial time derivative of ex and plus the curl of b x component is equal to 4 pi over c j1, right? Okay, so now we can write the equation in terms of this on the left hand side, and so what that would be is curl of bx component is equal to 4 pi over c j1 is of course your x component of j, then we have plus this term over here, that is plus 1 over c partial time derivative of ex, right? So if you look at this equation, it has all the x components, but in general we can write it directly as the curl of b, right? So as a vector. So let's go ahead and do that. What we would have is then generally we would have curl of b is equal to 4 pi over c j plus 1 over c time derivative of my electric field E, right? So in the vector form, right? And so then this equation is also one of the Maxwell's equation. If we go back to first page, so this equation is then the fourth Maxwell equation, that is this one over here, right? So we were able to derive two of the Maxwell's equations with the help of the electromagnetic field strength tensor, right? So one of the equations was of course the Gauss law, and the other was the that is this one is the Ampere's law, with the Maxwell's correction term, of course, that is the electric field, right? Okay, so now we may write the field strength tensor in covariant form as this thing. So F alpha beta is equal to the metric tensor alpha rho F rho sigma g sigma beta, right? Okay, so all I have done is I have written the contravariant form of the strength tensor as in my covariant form, right? So the indices have shifted. Okay, so let's find one component of my covariant form of the field strength tensor. So let's say that we want to find F01, right? So what would that be? So alpha is 0 and beta is 1, remember that. So we would have G, alpha is, remember, 0, and we have rho, then we have F, we have rho sigma G sigma, and this beta is 1, so 1, right? And so when we open all of this, all of the components would cancel out or vanish except for the components that are G00, F01, G11, right? And you can expand this, right, from all of these variables going from 0, 1, 2, and 3. And what you would see is that you already know that whenever your f, the indices on your f are equal, that is from here, this one. So when these indices on f are equal, you would get all of these 0 components, right? So you would have 0 for them. And you also know that whenever your for the metric tensor, when your g, let me write it down here, g, let's say alpha beta, right? So when alpha is not equal to beta, this thing over here is 0, so this vanishes. So using these two conditions, you can expand this expression over here, and you would see that all of the components would vanish except for this one over here. And so what is this, right? So G00 is my +1, again in the particle physicists metric tensor notation. And I have F01, and G11 is -1. So that's the spatial component. This was the time component, and this is the spatial component. Right, and so what this gives me is, of course, that my F, covariant F01 is actually equal to EX, right? So this is -EX, and multiplied with this -1, it gives me positive EX, right? Okay, so likewise we could obtain all of these components, right? So you could obtain the covariant components for the field strength tensor, right? And so again, I would like to recommend that you do this as an exercise yourself, and pause this video here and try to figure out all of these components. Right, okay, so now moving on, the covariant field strength tensor in the matrix form then can be written as, assuming that you have figured out all of these components, I'm just directly going to write it down. So F alpha beta is equal to 0 EX, EY, and EZ. And now for the E minus EX, 0. Again, we have the diagonal terms, all of them as 0, right? So we have minus BZ, BY, minus EY. So these are all of these components that I asked you previously to figure them out yourself as an exercise, right? So if you did that, you can now check your answer from here. Okay, so you have B negative BX over here, negative EZ, negative BY, BX, 0. Right, so then this is your covariant form of the field strength tensor. Now note that the elements of this covariant field strength tensor are obtained directly from the contravariant field strength tensor by simply replacing your E with negative E, right? So if you replace that in the contravariant field strength tensor, you replaced your E with negative E, you would get the elements of F alpha beta, that is this one, the covariant tensor, right? Now, if you look at the magnetic components, they did not change, right? They remained the same, and that is because, let's go here and let's work out those, as F12 is equal to G1 rho F rho sigma G sigma 2, right? Now again, if you expand these components, right, the only components that would survive are G11, F12, G22, right? And what would that be equal to? That would be equal to G11 is now -1, right? Sorry, -1. F12 is my negative BZ, right? And then again G22 is -1. So what would this give me is negative BZ. And so if you go back and look at the contravariant form of the field strength tensor, F12 was still negative BZ. So the magnetic components did not change from going from contravariant to covariant field strength tensor. Right. Now we are done with the electromagnetic field strength tensor. Next step is to use another useful quantity that is called the dual field strength tensor. And the dual field strength tensor, dual field strength tensor, right? This tensor is defined as F tilde alpha beta being equal to 1/2 this thing that is this thing is what I'm going to write down is called the Levi-Civita symbol, right? And it is a totally anti-symmetric fourth rank tensor. So it is E alpha beta rho sigma, and then we have F rho sigma. So this is how we define the field strength tensor, right? Okay, so this is the definition. Now this totally antisymmetric fourth rank tensor that I wrote with epsilon alpha beta rho sigma is also defined, and it is defined as, let me write it down over here. It is defined as epsilon alpha beta rho sigma. It is equal to, now it's equal to +1 for when we have alpha is equal to 0, beta is equal to 1, rho is equal to 2, sigma is equal to 3, right? Which is any even permutation, right? And it is -1 for any odd permutation. So odd permutation, right? And it vanishes for any repeated indices. So if we have indices that are repeated, this tensor would vanish, right? So it's for 0 for repeated indices, right? So if any of these alpha, beta, rho, and sigma would be repeated, the tensor would vanish, right? Okay, so let's look at the case where we have alpha is equal to 0 and beta is equal to 1, right? So let me write it down over here. For alpha is equal to 0, beta is equal to 1. Well, if we go back over here, look at the definition of the dual field strength tensor, we can then substitute in here for alpha is equal to 0 and beta is equal to 1. And substituting these two values for alpha and beta, then we would see the corresponding rho and sigma, right? So let's go here and let's do that over here. Okay, so F tilde 0 1 is equal to 1/2 of my epsilon. Now alpha is 0, beta is 1. Now what could we have for rho and sigma, right? So we could have 2, 3, right? And so if rho and sigma are 2, 3, then F rho sigma would be F2, 3, right? And likewise, then we could also have this term where we could have epsilon 0, 1 for alpha and beta. Now rho and sigma, rho could be 3 and sigma could be 2, right? So that would be 3, 2, right? And so if rho and sigma is 3, 2, so there would be F3, 2 over here, right? So now let's simplify this, and then we would have here 1/2, and this, because we have even permutation, that is 0, 1, 2, 3, we would have this thing as positive 1, and we already know that F2, 3 is negative bx, right? So the x component of the magnetic field, plus 1/2. Now this quantity over here, this tensor, this would be -1 because we have odd permutation, right? So we have 0, 1, 3 and 2. So for that we have -1, right? And again F3, 2 is because this tensor is anti-symmetric, this field strength tensor, so we would have positive bx, right? And so if you now add these terms, so 1/2 plus 1/2, and we have a negative bx and negative bx, so half goes away and we are only left with negative bx, which is of course our 0, 1 component of the dual field strength tensor. Now likewise you could figure out the 0, 2 component of the dual field strength tensor. That would be nothing but your negative by, and your 0, 3 component of the dual field strength tensor would be negative bz, right? So you could work out these components yourself, and again that would be a very good thing to do, right? Okay, so now we should also look for when alpha is equal to -1 and beta is equal to 2, right? So what would those components be? Okay, so for alpha is equal to 1 and beta is equal to 2. I'm sorry, I might have previously just said that alpha is equal to -1. What I meant was alpha is equal to 1 and beta is equal to 2, right? Okay, so now with that I have my dual field strength tensor F12 as equal to 1/2 epsilon 1, 2, 0, 3 F03, right? I'm again doing it in a similar manner how I previously did over here for alpha 0 and beta 1, right? So we're following the same procedure. We have alpha 1, beta 2, so we have 1, 2 over here, and alpha 1, beta 2, rho and sigma would be then written correspondingly, right? Accordingly. Okay, so we have 1/2 epsilon. Now we would have 1, 2 instead of 0, 3. Now we would have 3, 0, right? And of course F, now we have 3, 0 over here, so we would have F30, right? Okay, so when you solve this, what you get is F tilde 1, 2 is equal to the z component of your electric field, right? So you have to just simply see what your F03 was from your covariant field strength tensor, and F30 as well, and again you use the definition of this Levi-Civita symbol to figure out what this would be. Okay, so now again you should work out all the rest of the components yourself, and once you do that, the matrix representation would be F tilde alpha beta is represented in a matrix form as over here. So we have 0, and likewise again the diagonal components would just vanish, and so we would have Bx By Bz, right? And we would have over here negative Bx 0 negative Ez Ey negative By Ez 0 and negative Ex. And finally over here we would have negative Bz negative Ey Ex and 0, right? So now the elements of the dual tensor are obtained from the field strength tensor, right, the contravariant form of that, by simply replacing E with B and B with negative E, right? Okay, now let's look at the remaining two Maxwell's equations, and they can be obtained or recovered with the aid of the dual field strength tensor, right? So let's go ahead and do that over here. Okay, so again we have Maxwell's equation can be written as partial alpha F tilde alpha beta, now the dual field strength tensor, and this is equal to 0. Now again we will have to substitute first for beta is equal to 0. Once we do that, we would have partial alpha F tilde alpha 0 is equal to 0, right? And now again we would be summing over the repeated indices, and what would that be? That would be partial 0 F 0 0, right? And of course we have this as this is the field dual strength tensor. Then we have partial 1 F tilde 1 0 plus partial F tilde partial 2 F tilde 2 0 plus partial 3 F tilde 3 0, and this is equal to 0. Okay, now again we know that this first this one component would vanish because F00 is simply 0, and now the other components, this partial 1 would give me partial derivative with respect to x. F tilde 10 was Bx, right? It is from here, this matrix or the components that you could just figure them out yourself, right? And so now plus partial 2 means partial derivative with respect to y. F20 is again the 20 component, which is nothing but By, plus partial 3 is partial z, and that other component for F tilde is simply Bz, and all of this is equal to 0. Now again this over here is the definition of my gradient of B, right, and this is equal to 0. Now this over here is the also one of the Maxwell's equations, right, that is the gradient of B vanishes. So we have again recovered another one of the Maxwell's equation with the help of the dual field strength tensor. Right, now finally let's go ahead and substitute for beta is equal to 1, right? And once you do that, what you get is partial alpha F tilde alpha 1, right? Now what is this equal to? Again, we have to sum over the repeated indices. So partial 0 f tilde 0 1 plus partial 1 f tilde 1 1, right, plus let me write it down again, plus partial 2 f tilde 2 1 plus finally partial 3 f tilde 3 1, and of course this is equal to 0. Now if you look at this equation again, this f11 would vanish, and so this whole term would go to 0. Now this partial 0 is, we know already, it is 1 over c times partial time derivative, and f01 is nothing but negative bx, right? So let me write it down, negative bx, and then partial 2 is partial derivative with respect to y. f21 is my negative ez, right, and plus partial derivative with respect to z of ey, because this f tilde 31 is ey, and of course this is equal to 0, right? Okay, so now all of this can be written as this negative sign will come outside, so I would have negative 1 over c partial time derivative of bx, and let's take outside the negative sign. We would have a negative sign over here as well, right, with this ey, right, because if you go back, f31, so f31 is then this over here. Oh no, I'm sorry, f31 is this thing over here, right? So it's just ey, so we would not have any negative sign over here, so this would be plus, right? So it's plus ey, right? Okay, I'm sorry, forgive me, this video is a bit too long, and now I'm getting kind of confused, but yeah, that this thing over here is plus ey, right? And so if that is plus ey, what I can do is I can take a negative sign outside, and I can write then this whole thing as my curl of E, right? So this can be written as curl of my field E, right? And of course the x component of that. Now with this I have this thing equal to 0, and so then I can write the equation in terms of this, but if I consider all of the vectors, right, so that would be the curl of E is equal to negative 1 over C partial time derivative of my magnetic field B, right? Okay, so right, I made a mistake again over here. This would actually be positive, right? And so you would get this equation. No, actually, I'm sorry. It would be negative, right? Okay, so we have finally, with the aid of the dual field strength tensor, recovered the last Maxwell's wave equation as well, right? So finally we are actually now done with deriving the electrodynamics in the tensor notation, right? We have received or recovered all of the Maxwell's wave equations with the help of the field strength tensor and its dual field strength tensor. So these two tensors have then been useful to reproduce all of the four Maxwell's equations, right? And so the tensor formalism led to mathematically simpler presentation of the physical laws, right? And those physical laws in this case are the Maxwell's laws, right? So the Maxwell's equations. And we can visually see that it had simplified the laws, right? Because we had four Maxwell's equations and we were able to reduce them down to simply just two tensors, the field strength tensor and its dual field strength tensor. And with the help of these two tensors, we were finally then able to reproduce all of the four Maxwell's wave equations, right? And of course, now as physicists, we try to avoid the complex and silly mathematics, right? And so this tensor formalism is extremely helpful for us physicists, right? Okay, so that's it for this video. It was a bit too long and I might have stuttered in between because I did not even take a break, right? So I hope that you were able to follow along with the video, and if you have questions, you could leave them down in the comment section below. What I would recommend you all is to sit down and watch the video, and as you're doing that, take a paper and a pencil and start doing these calculations by hand, right? So pause the video and perform the calculations, for example, wherever you have to compute the components of the tensors, or you have to see what this equation is, or why does this equation becomes this thing or that thing, right? So it is highly recommended that you sit down and compute all of these things yourself while you watch the video. So you could pause it in between and you could compute for the components of the tensors, right? Okay, so with that, I'm going to end this video now. So I hope you enjoyed and you got a bit of understanding of the tensor formalism of electrodynamics. So with this now, the series on the tensor formulation of electrodynamics ends.